Hi, my name is Brian Jackson. Today I'll be talking about planning with attitude. So a lot of the robotic systems that we know and are familiar with move and operate freely within three-dimensional space. So these could be quadrotors, airplanes, underwater vehicles, or space systems. So one of the principal challenges in dealing with any of these robotic systems, especially when we're trying to generate optimal motion plans, is dealing with the group structure of 3D rotations. So while I don't think I need to motivate too strongly why unit quaternions are an excellent choice for representing 3D rotations, one of the key points I want to drive home with this presentation is that unit quaternions are linear operators. So this stems from the fact that the space of unit quaternions is isomorphic to the space of R4, which is really just like fancy talk for saying that a lot of the common operations that we do with unit quaternions ends up being end up being linear algebraic expressions or just matrix vector multiplications. So this ends up being very nice when it comes time to doing calculus on the space of quaternions. So why do we care about this? Oftentimes in robotics, and particularly with optimization-based approaches, we want to take first or second order Taylor series expansions with respect to our nonlinear functions. So the question that we pose is, how do we do this effectively and efficiently when the input or output is a quaternion? So how do we evaluate Jacobians, gradients, or Hessians for these types of functions? So the key takeaway here is that, or the key idea is that the space of differential rotations lies in the plane tangent to the space of unit quaternions. So the space of unit quaternions is a ball in R4, and the differential rotations lie in a plane tangent to that ball. So there exists a nonlinear mapping between the our differential values and the values of the group. So in practice, when it comes time to take a derivative, what we want to do is we want to evaluate the effect that a differential value applied to the input has on the output. So when we want to take a Taylor series expansion, all we have to do is take the chain rule through this, accounting for the composition rule for the group, which ends up just being a nice left matrix multiplication. And then we differentiate through this nonlinear map, evaluated as the differential value goes to 0. So doing this for any of the maps that we looked at, in particular the Cayley map or the exponential map, up to a constant scaling factor, they all end up resulting in the same Jacobian, which we call the differential or the attitude Jacobian. In practice, this ends up being a very nice conversion factor between the results we would get treating Q as a vector in Euclidean space and accurately accounting for the group structure of rotations, including the reduction in dimension for a unit quaternion. So here's a couple of very nice and simple rules for how to do this in practice. To show that this actually works, we'll apply it to Newton's method on the space of unit quaternions. So here's a very simple nonlinear least squares problem. Could be, say, for example, a state estimation problem. We then want to take the Jacobian of the residual function with respect to Q, treating Q as a vector. This ends up being very nice in practice because we can use any of the methods that we know and are familiar with, such as automatic differentiation or finite differencing, or just doing it by hand. We then take that very straightforward result and then multiply it or convert it using this attitude Jacobian, which maps us into the space of differential rotations. We then compute a step in the space of differential rotations, and then obviously convert that step back to the space of unit quaternions and compose it with our current iterate to get the next one. So we obviously apply this iteratively like we do in Newton's method, and with this method, we recover the full quadratic convergence of a Newton's method that we'd expect. We compare this to a more naive approach that projects back onto the space of unit quaternions after every iteration. After just a couple iterations, the progress stalls. So we didn't stop here. We went ahead and applied these same tricks to our full nonlinear trajectory optimization solver called Altro. So here we got a pretty good improvement in terms of speed and the number of iterations on a series of problems. Here's a fun little example trying to do a quadrotor flip trajectory. Before, it didn't really work, but by kind of making these changes in the underlying guts of the solver to correctly account for the group structure rotations when we take derivatives, we were able to converge to a pretty nice trajectory pretty quickly. So So in conclusion, we presented a very straightforward method for adapting existing gradient and Newton-based algorithms to correctly account for the group structure of rotations. And this is actually very nice because it's built on the principles of linear algebra and vector calculus, which should be very familiar and accessible to pretty much everyone in robotics. So with that, happy to take any questions. Thank you.